Okay, so here we're going to talk about heaps, and in the Xi book, they talk about a max heap. You can also, when you talk about using a heap sort, have min heaps. The max heap that's demonstrated, the largest element is going to be the root of the heap. And a lot of times it's good to be able to find the largest value on certain applications, and that's where a max heap would come in useful. So a max heap is just a binary tree, right? So every node has at most 2 nodes that maintains a simple property that the node's key is greater than or equal to the node's children. So every parent has to be greater than both its children. Greater than or equal to, let's say. But in my example, I'm just going to use, I don't have any 2 that are the same. Okay, so I'm going to insert these values, 22, 55, 99, etc., into a max heap. And you just start with the first value, 22. So when you start, that'll be the root. And next is 55. Now for a max heap, you've got to keep it complete. So it's going to have to go in this location right here, 55, to the left of 22. But then remember the property. You have to look at it. This element here has to be less than its parent, and it's not. So you're going to exchange those two. Now remember that, we're showing this as a tree, but it's really super efficient to store these in arrays. So like this particular little max heap would look like that. Okay. The next element is 99, right? So we're going to put 99 here because you got to keep it complete. So it's got to go in the next available location. And then you got to compare 99 to its parent. It's greater than its parent, so here we're going to exchange these. Okay, so like you would do this in the array. And I'm not going to keep drawing the array, but I just want to show you. So now my heap looks like this. Okay. Now we have 66 has to go to the left of 22. You compare it with its parent. It's bigger than its parent, so you exchange those two. And you have to keep going up. You have to compare 66 with its parent, and they're okay. So now we have 11. That's going to go here. We compare it to 66, its parent, and those guys are fine. Then we have 33. It's got to go here. You got to compare it to its parent, 55. Those are okay. And then we've got 77 is going to go here. So 77 has to be compared to its parent, which is 55. And they're out of order, right? So you're going to exchange those, but then you've got to look at 99 and 77, and those are okay. All right, so this is getting a little crowded. Let me just redraw my heap so you can see what's going on. And next we have 44. So 44 has to go here to keep it complete. When I compare it with its parent, they're out of order, so I'm going to exchange. And then you need to look at 44 and 66, which are okay. And lastly, we've got 88. So that's got to go here. When you compare it to its parent, it's out of order. So 88 goes here, 44 comes down here. 88 gets compared to its parent, 66, and those guys are out of order. And now 88 gets compared to its parent, 99, which is okay. So our final max heap looks like this. And the only thing true about a heap is that the largest, every node is bigger than both its children. So 99 is, 88 is bigger than both its children, 77 is bigger than both its children, 66. That's the wrong, that should be 44. Sorry, that's me writing that wrong. And then remember, you could store it as a tree, but it's super easy to store this in an array because, as an array, it's a complete tree, so every element of the array is going to be filled up I'm running out of room. 44 goes at the end. Okay. And when it's in an array, it's easy using simple calculations. You know that the root's always at index 0. And there's easy calculations to find, the left child is always 2 times the index plus 1. So 2 times 1 is 2, plus 1 is 3, and that would tell you that 88's left child is at index 3, and it is. So when you look at things like this, like a left child is just 2i plus 1, right, where I is the index. A right child could be located at 2i plus 2, right? So if I is 1, 2 times 1 is 2, plus 2 is 4, and that would tell you that whatever's at index 1, its right child is right here. So really easy calculations, and that's how a max heap works.